Hey everybody, welcome to Conceptual Physics. Okay, thanks for the excitement today. So today we're going to talk about work, power, and machines, which is going to be a lot of what we do for the second semester. The objectives are to define work and power. We have our ideas on what work and power are, but scientifically the definitions are a little bit different. And then calculate work, and then we'll calculate power too. But not in this section. And then use mechanical advantage ideas to explain how machines make work easier or better, maybe not always easier, which will be important for when we do our mousetrap vehicles. And then we're going to be not just using mechanical advantage ideas, but we'll be able to calculate mechanical advantage in multiple ways. Okay, so first definition, what is work? Is the question. Work is the transfer of energy to a body by the application of a force that causes a body to move in the direction of the force. And so that would be a little bit confusing in one way. Like if I'm on a hill and I got something that I'm trying to keep up the hill, which I would never suggest to push a car up the hill, but maybe I have a wagon. And if I'm trying to push that wagon up the hill, I'm forcing in this direction, right? That's the force applied. But the force of the load is really in this direction because that wagon, it wants to go downhill, and we say wants, but it doesn't actually want like we want, but we say that, or I say that. But a wagon is going to go downhill, right? Unless you apply a force to it. But if that force of the load is bigger than the force applied, then what happens is this thing moves a distance or a displacement. So if we call this displacement the negative direction, what would we call the direction of the force applied? Positive or negative? Positive, right? Very good, because a force is a vector, and the opposites are opposite in sign. So what would happen in this case is the work of the person is going to be a negative number. And now work cannot be a vector, but work is describing the energy transfer and how the energy is affecting the situation. So work can be negative, but it doesn't mean direction because work is a scalar. Okay, so you better put that in your notes right away. Work is a scalar quantity, although you can have negative work, which means it's taken away from, like in this case, it's taken away from the kinetic energy. Because if something rolls downhill, it's going to go faster and faster and faster. But if you're grimacing and trying to stop that thing, you're going to slow it down. And so kinetic energy is energy of motion. If you have negative work, it takes away from that kinetic energy. Okay, so just a little more definitional stuff. Work is done only when a force causes an object to, well, this is exactly what we set up here, causes an object to move in the direction of the force. And the movement in the direction of the force isn't always happening. Like I said, if you have a negative work, then that's going to be opposite of the direction of force. So this is different from the everyday meaning of work. Here's the work equation. I'd just like to add this to it right here. This right here, parallel. So work is equal to the part of the force that's parallel to the displacement. It's equal to the product of those two numbers. The force that's parallel to the displacement. Okay, so you're probably wondering what that means, how that works. Let me explain that just a little bit more. So if I have a box on the floor and I'm pulling, so this is me pulling this thing, across the floor, right? So the displacement of the box is in that direction. The force applied is in a direction that's not parallel to the displacement. So you got to do, remember SOHCAHTOA we did last couple months ago? You got to figure out that part of the force that's applied, because that part, which is a smaller number than this, right? Because a squared plus b squared equals c squared. That part of the force is the part of the force that you multiply by the displacement in order to get the actual work. This part of the force is doing something too, but until we talk about friction, we're not really going to talk about what that part is doing. But it is lifting the box up. So it makes the interaction between the surface and the box less by this amount of the force applied. Okay, so here, work is measured in joules, and joules is a big J. That's a label. We have a big J that's part of a formula we're going to use too when we get into labs, but this big J is the label, not the formula. Work is calculated as a force times distance, so you could also say it's Newton times meters. It's another way to put the label, or you could just say big J. Joule, named after Jimmy Joule or James Joule. These units are called joules. A joule is equivalent to 1 kilogram meter per second squared. Definition of joules. That's a mathematical definition. Okay. Now, this right here, it says, meters squared per second squared, kilogram meters per second. So it's force times distance. A force is a kilogram times meters per second squared times another meter. That's how we get that meters squared there. Okay, so here's our first question. Imagine a father playing with his daughter by lifting her repeatedly in the air. How much work does he do with each lift, assuming that he lifts her 2 meters and exerts an average force of 190 newtons? Okay, so here's the daughter throwing the kid up in the air or lifting the kid up in the air. It's always a fun thing as a parent, right? It looks like the kid is having a good time because they got a smile on their face, but later in my years, I realized that maybe the kid's actually freaking out and getting scared. I don't know. I thought it was a good thing to do, but who knows? So here's the distance of 2 meters. And when I suppose this would be, you have to be touching the kid to be putting that force on there. So the force is 190 newtons. Okay, so work is force times distance, parallel. And is it parallel? Yeah, because the kid is going up and down. The force has to go up in order to move this kid upward. So it's 190 times 2. The work is 380 joules. Okay, so power is another thing here. And power is just defined as the rate of work. And so it's a kind of a fun little lab that I like to do with you guys, is figure out who the most powerful kid is in class by running up the stairs as fast as you possibly can. And so power then is work per time. So anytime you see this word rate, it means per time. And for us, it's going to be seconds. You could also write it as force parallel displacement per time, but that's power. So when we talk about power, we're always talking horsepower, right? But when we do science power, it's watts. That's the label for your power is watts. Okay. So here's a little example of that. So it says it takes 100 kilojoules of work to lift an elevator 18 meters. I'm going to turn this into a joule instead of kilojoules. So you multiply that by 1,000, right? So 100,000 joules to lift an elevator 18 meters in 20 seconds. What's the average power? Okay, so power is work per time. Power is force times a parallel displacement per time. Okay. So power is then the force is, oh, I guess the force and distance here is already done for us because this is the work. So that's 100,000. Oops. So that's 100,000 divided by 20 seconds. Okay, Preston, do you got that in your calculator? 100,000 divided by 20? Yeah, so it's 5,000 watts. Now, this is a little bit of a funny question because it asks for work. It asks for power, which we know is work per time. It gives you work, but it also gives you this distance. So it's a little bit confusing, but you don't have to use that distance because you already had this whole multiple here where it's force times distance. You already had that in your work answer. So 5,000 watts should be the right answer. Okay, so yeah, the PowerPoint actually comes up with the same answer, but it comes up with an answer in kilowatts, which means 1,000. So 5,000 watts is the right answer. Okay, so we're only halfway done with the PowerPoint, but I think it's time to do a little lab on power. So I hope hopefully you paid attention to that last video here. This one about how to do power calculations, because we're going to go out and put that understanding to work. We're going to go out and we're going to see which of you are the most powerful by running up the steps. Okay, so we're going to do a quick lab. Power rate of work, it's called. Have a good day.